Far beyond Earth's noise, a third interstellar visitor, 32 Atlas, is racing toward Mars. It's just days from a flyby, so close that every agency should be sounding alarms. But instead, mission feeds are falling silent. Official voices have vanished, and the object's path? It slices almost flat through our planetary plane, something no ordinary comet should manage. With its trajectory locked, a corridor just 5 degrees off the solar system's disk, and a hyperbolic speed, it's cutting through familiar territory as if on purpose. Why have the world's telescopes gone quiet as 32 Atlas heads toward Mars fast? And what happens if the truth is more extraordinary, more unsettling than anyone is admitting? The silence only grows as the encounter approaches. Mars, silent and red, drifts just 18 million miles from the inbound path of 32 Atlas. That's close enough for its orbiters to catch every detail, if anyone was watching. But the official feeds from Mars Express and the Trace Gas Orbiter remain nearly blank. There are no press bulletins, no mission updates. The raw data streams, usually so eager to showcase Martian dust storms or seasonal frost, now show only routine science. There's no mention of the interstellar visitor threading through their skies. Inside mission planning rooms, schedules have shifted. Instrument teams are quietly reworking observation windows, squeezing in high-resolution passes and retuning spectrometers for water, ice, organics, and isotopic fingerprints. Yet, these changes pass without public notice. The only hints come from technical logs, buried timestamps, and subtle tweaks to target lists, while the world's attention stays fixed on other news. The flyby window is measured in days, not weeks. At its closest, 32 Atlas will streak past Mars at a velocity of over 61 kilometers per second. Its coma and tail will be faintly visible to any camera pointed in the right direction. For comparison, the last interstellar object, Borisov, never came within 150 million miles of a planet. Now, a cosmic visitor cuts nearly 5 degrees above the solar system's plane, threading a corridor that brings it within striking distance of Mars. It's a geometry so flat and precise that orbital analysts call it mission-like. Yet, the silence holds. No agency steps forward to brief the public. The usual parade of mission scientists, so quick to claim discovery or warn of risk, has gone quiet. Even the amateur networks, those sleepless, camera-toting observers who once lit up Discord and Telegram with every new comet, find themselves starved for updates. The encounter is days away, and the only certainty is that the world's best-positioned observers are saying almost nothing. The question lingers. In a solar system built on open science, what does it mean when the closest witnesses choose not to speak? July 1, 2025, on a quiet night in the southern hemisphere, the Atlas survey in Chile flagged a faint, fast-moving object in its automated scans, one that didn't fit any known solar system track. Within hours, the alert reached orbit analysts across the globe. By dawn, the Minor Planet Center had logged the first astrometric data, and the search for earlier images began. In the digital archives of the Zwicky Transient Facility, a handful of frames from June 14th showed the same streak, hiding in plain sight weeks before its official discovery. Each new data point tightened the orbit, and the numbers told a story that left little room for doubt. This was a visitor from deep space. The orbital solution came together in a matter of days. An eccentricity greater than 1. A hyperbolic excess velocity clocked at 58 kilometers per second inbound. The inclination, just under 5 degrees from the ecliptic, stood out. Most interstellar objects cut steep angles through the solar system, but 32 Atlas was different. Its path hugged the plane of the planets, a corridor so flat that the projected trajectory would thread the inner solar system with uncanny precision. Mars, Earth, Venus, and Jupiter would each lie within a narrow band of approach, as if the object was tracing a route mapped by a mission planner. For orbital dynamicists, this wasn't just rare, it was nearly unprecedented. Simulations showed that out of thousands of random interstellar entries, only a handful would produce such a coplanar, multi-planet sequence. The Atlas team, led by seasoned survey astronomers, handed off their data to orbit modelers and statistical specialists. Each ran Monte Carlo ensembles, propagating the solution backwards and forwards across millions of years. The results were definitive. No prior solar system binding. No plausible Oort cloud origin. 32 Atlas had entered from the galactic field, unbound by the sun on a trajectory that would never return. The odds of this corridor-like path, less than 1 in 500 for known interstellar populations, added weight to every subsequent calculation. For the scientific community, the stakes were clear. An interstellar object, confirmed by both archival and real-time data, was about to sweep through the heart of the solar system. Its low-inclination hyperbolic orbit set the stage for everything that followed: a close pass by Mars, a series of planetary encounters, and a growing sense that this was no ordinary comet. The facts were in, and the questions were only beginning. At 6.4 astronomical units from the Sun, far beyond the frost line, 3.2 Atlas lit up. That first spike in brightness, flagged by Southern Hemisphere photometry teams, broke every rule in the comet playbook. Water ice shouldn't sublimate at that distance. Yet the light curve rose, fell, and rose again in a pattern that looked less like steady outgassing and more like a heartbeat. Episodic bursts, each lasting hours to days, gave the object a breathing rhythm. The numbers didn't lie. Amateur and professional observers, linked by Discord and late-night Slack channels, watched the magnitude jump by half a point, then fade, then leap again. No ordinary comet pulses like this. Dust physics offered another puzzle. High-resolution imaging from Chile and South Africa revealed tail segments curving sunward against the expected flow of solar wind. The standard model predicts light, fast-moving dust streaming away from the sun, forming a classic anti-solar tail. But here, the tail was kinked, with dense clumps lagging behind and at times bending forward. Spectral analysis showed a dominance of heavier, slower-moving grains particles that should have settled quickly or failed to escape at all. The geometry of the tail, mapped in detail by photometric analysts, defied simple explanations. Some suspected magnetic effects, others pointed to volatile pockets venting in jets, but no consensus formed. The light curve, when plotted over weeks, didn't smooth out. Instead, it flickered. Each burst revealed a fresh outflow of gas and dust. Each lull suggested a pause or a seal forming over an active vent. The amplitude and timing of these pulses matched neither solar rotation nor any known periodic driver. The object seemed to be responding to internal triggers, not external heating. The combination of its precise, flat trajectory and its bizarre, rhythmic activity painted a picture that was deeply unsettling. The closer it got, the more questions it raised, and the quieter the official channels became. It wasn't just a comet anymore. It was an anomaly, a mystery heading straight for our planetary neighborhood. And as the day of the Mars flyby approaches, we're left to wonder what the silence is hiding. For astronomers, the arrival of Comet 3I Atlas meant sleepless nights. They were chasing unpredictable outbursts, constantly recalibrating their equipment to catch the next surge of activity. For theorists, it was a race back to the drawing board, revisiting everything they thought they knew about interstellar ice chemistry and thermal stress. This wasn't just another comet. It was rewriting the rules. By the time Atlas reached the orbit of Jupiter, something was already off. The ratio of dust to gas was skewed. Mass estimates, based on the brightness of its coma, the fuzzy cloud around it suggested more material was spewing out than its size could possibly account for. The numbers just didn't add up. Some teams argued for a much larger, more volatile core hidden inside. Others wondered if the comet was already breaking apart, or if hidden caverns beneath its surface were driving the excess activity. The only thing everyone agreed on was that standard comet physics couldn't explain what they were seeing. This forced a massive shift in the scientific community. Professional photometry campaigns ramped up, moving from routine surveys to high-cadence, multi-band monitoring. Instruments designed to detect water, carbon monoxide, and organic signatures worked overtime. Observers logged every single jump in brightness, every anomaly in its tail, feeding a growing suspicion that 3I Atlas was no ordinary icy wanderer. Its behavior was off-script from the very beginning, demanding new tools, new eyes, and a willingness to follow the data no matter where it led. Behind the scenes, the world's most powerful telescopes were put on high alert, though few would admit it publicly. At the European Space Operations Center, controllers for the Mars Express mission quietly slipped new coordinates into the week's observation plan. Spectrometers on the Trace Gas Orbiter, usually pointed at Mars to look for methane and water vapor, were redirected. They began scanning the comet's coma for organics and rare isotopes. Each adjustment was buried in technical bulletins, never in press releases. The changes were subtle: an extra pass here, a shifted observation window there, but together, They formed a secret campaign, built for speed. On the other side of the solar system, the James Webb Space Telescope carved out precious hours from its jam-packed schedule. A fast-track proposal pushed JWST's powerful instruments into play, searching for the chemical fingerprints of pristine molecules, organics, silicates, and carbon monoxide preserved since the comet's journey between the stars. Reviewer notes, visible only in summary, called it an unprecedented opportunity. But even JWST had its limits. A blackout window was looming, and the telescope as sunshield couldn't bend enough to track the comet during its close pass by the sun. Hubble's directors also authorized a series of high-cadence imaging runs, focusing on the bright halo of dust and gas surrounding the nucleus. The early results only deepened the mystery. The mass of ejected material, inferred from the coma's brightness, far exceeded what the estimated size of the nucleus could explain. If the core was really less than 6 kilometers across, as direct imaging suggested, then something other than solar heating had to be driving this incredible outflow. Some teams argued for hidden reservoirs of volatile ices, or even that the comet was actively fragmenting. Others urged caution, pointing to the huge error bars that always plague comet science at such vast distances. While the official institutions scrambled, a global network of amateur astronomers became the backbone of continuous monitoring. In South Africa, Chile, and Australia, coordinated teams raced the sunrise, logging every outburst. Discord servers and Telegram channels lit up with raw data photometry, spectral snapshots, and time-stamped jumps in magnitude. Rivalries flared over calibration methods and equipment, but the data flow was relentless and invaluable. When the coma flickered or the tail developed a strange kink, it was often the amateurs who spotted it first, sometimes hours before the professional alerts went out. As the blackout window approached, every single observation became critical. Soon the Mars orbiters would be the only eyes with a clear view. Hubble and JWST would have to stand down, their solar avoidance protocols locking them out of the action. For a brief tense period, the fate of the entire observation campaign would rest on a handful of aging spacecraft and the resolve of a scattered community all watching for signs that this visitor was more than just another comet. The clock was ticking, and the data stream had become a lifeline. In the weeks before perihelion, the comet's closest approach to the Sun, the official silence grew heavier. Scientific preprints dried up. Conference sessions that were once open suddenly closed their doors. Technical notes, previously routine, were now stamped with phrases like operational security and internal review only. Astronomers, who once freely traded messages about filter choices, now spoke in careful code, or simply not at all. A few leaks surfaced. Snippets from mission chat logs, a redacted email chain with the subject line, "Data embargo until further notice." Even the usual flood of raw images from Mars Express slowed to a trickle. The data existed, but access was being restricted, sometimes for days at a time. Inside these quiet corridors of science, frustration simmered. Professor Avi Loeb and his circle of intercept advocates pushed hard for a last-minute flyby mission. They argued that NASA's Juno spacecraft, already near Jupiter, could be repurposed for a close pass. The answer from the top was swift and final: not feasible. Budget lines were cited. The risk to Juno's primary science mission was invoked. In one leaked Slack exchange, a project manager wrote, "Not a chance. Mission priorities are set. No delta V to spare." The proposal died in committee, never even reaching public debate. Meanwhile, whispers and rumors spread through the amateur networks. Another Slack leak hinted at a technical anomaly, but the details were scrubbed before they could reach wider channels. For every rumor, there was a counter-rumor. Was the data being held for a coordinated bombshell release? Or was it embargoed simply to avoid misinterpretation? The blackout window was coming, and with it, a gnawing sense that the most important data might remain locked behind closed doors. For now, the halls of planetary science were quiet. Too quiet for comfort. By late September 2025, the final countdown was underway. But for Earth-bound astronomers, the show was about to end. As 3I Atlas closed in on the Sun, its apparent separation from our star dropped below 15 degrees, rendering it lost in the blinding glare of daylight. Hubble and JWST, with their strict solar avoidance rules, entered a forced downtime. Their observation logs, so recently filled with urgent notes, went blank. For nearly 2 weeks, the world's most sensitive telescopes were completely blind to the interstellar visitor, right at the moment of its peak activity. Mars, trailing just 18 million miles behind the comet, became our lone vantage point. Mars Express and the Trace Gas Orbiter, spacecraft never designed for comet tracking, squeezed in whatever observations they could. Their controllers, working in the shadow of institutional silence, rotated spectrometers, retasked imagers, and pushed every kilobyte of data through the thin window before solar interference disrupted communications. At the fringes of the sun's glare, the SOHO and Stereo spacecraft stood ready. Their coronagraphs, designed to block the sun's direct light, might catch a glimpse of Atlas as it skirted the edge of their view. But these are indirect eyes, sensitive only to brightness, not the crucial molecular fingerprints or dust grain velocities that had made the early campaign so compelling. The data stream, once a flood, had narrowed to a trickle. The blackout was total. For the first time since its discovery, the story of 3I Atlas was continuing beyond our reach. The world was left waiting and wondering. October 31st, 2025, perihelion. For months, the debate had circled around one stubborn question: just how big is the heart of 3I Atlas? Early Hubble and JWST imaging had capped the nucleus at under 6 kilometers. But as the comet neared Mars, the numbers kept climbing. Some models, driven by the sheer mass of dust pouring from the coma, now argued for a core up to 10 kilometers across. If true, it was a behemoth among interstellar visitors, and the implications rippled through every possible scenario. Modelers raced to map the final outcome. 3 fates dominated the discussion. The first was fragmentation, which would scatter debris along the orbit, each shard a window into the comet's hidden structure. The second was a dramatic flare and explosive surge of gas and dust that could signal a total collapse or a volatile-rich core giving up its secrets in one violent act. But the third possibility, survival, would raise the sharpest questions. If 3IATL aced past perihelion intact, its strange low-inclination path undisturbed, theorists would be left to explain not just its strength, but its trajectory. Was it natural, or was it something else? Mainstream teams leaned toward a volatile-rich interstellar comet, its oddities chalked up to buried ices and unfamiliar chemistry. Yet, a vocal minority kept the mission profile hypothesis alive, pointing to the eerily precise trajectory and the rhythmic, episodic outbursts. For now, the nucleus remained hidden in the sun's glare, shrouded in speculation. Its final act was waiting in the solar fire. Despite the intense scrutiny, key questions remain unanswered. What caused its rhythmic activity? What is the nature of its unusually dense dust grains? And why do its mass and coma size diverge so sharply from established models? With Earth-based observation paused, only the Mars orbiters and solar observatories maintained a partial watch. The evidence leaves one fact clear: 3ITLAS has challenged standard cometary science and exposed deep gaps in how our scientific institutions communicate extraordinary data. What really happened at perihelion and what this object truly is remains a matter for future archives to resolve. Thank you for watching. If you found this journey as fascinating as we did, don't forget to like this video and subscribe for more deep dives into the mysteries of our universe.